Welcome everyone. My name is Christian Wurzer. I'm a PhD student at the UK Biochar Research Centre, and I will talk today about one of my projects about the influence of iron doping using iron-rich waste on biomass pyrolysis and biochar performance. So first of all, I will talk a little bit about the background from this study. So about carbon adsorbents in wastewater treatment. So that's the application I'm designing them to be used later on. Then about magnetic biochars, before I will talk about the experimental setup and the results from my study. So I'm working with emerging contaminants, and for those of you who are not familiar with the term, emerging contaminants are micropollutants which are found in trace levels in water bodies, so something like surface water, groundwater, even drinking water. And these micropollutants are usually ranging from being pharmaceuticals, personal care products, herbicides, pesticides. So quite a range of different pollutants. And the first question is, how do they get into our water? So on the left, you can see these symbolic figures of the main pathways of micropollutants into our water. First of all, pharmaceuticals, we all take medicine, and one specific about pharmaceuticals is that once you take them, you only metabolize a certain amount of it. The rest will be discharged into the water, so you flush them directly down the toilet. That can be up to 80% for certain pharmaceuticals. So that's the main pathway here. Another contributor to pharmaceutical contamination is from livestock farming, especially cattle farming, because they use in industrial livestock farming, they use huge amounts of antibiotics, and they get also directly discharged into the water after their use through the cattle. And for herbicides and pesticides, the same issue arises for agricultural farming. So you use a pesticide on your soil, it rains, and the runoff will directly go into the water body, or not directly, but indirectly after it passes the soil. So once the pharmaceuticals come to the into the wastewater, there are two possible pathways. The first one is that in the case of livestock farming or agriculture, it will directly be discharged into the environment, so into the water cycle. And the other pathway is for human consumption, for example. So not human consumption, the urban wastewater treatment, which is usually treated in a treatment plant. So here and then the discharge from the wastewater treatment plant will again end up in the environmental water cycle. And the issue with emerging contaminants is that even trace amounts of these contaminants, so we are talking about micrograms or nanograms of per liter, they present unknown risks in the environment. So this ranges from behavioral changes for aquatic microorganisms, not microorganisms, aquatic life, to antibiotic resistance genes, and a lot of unknown problems there. So what I'm interested in is the pathway through the wastewater treatment plant, because that's the place where a biochar filter can be used. And if we look further into a wastewater treatment plant, so how these operate to date. So you have your wastewater influx, and then you have a primary treatment, which is used to remove solids through coagulation and flocculation. And then you have, so that removes inorganic pollutants mostly. And then it goes to the secondary treatment, which is biological treatment usually, so anaerobic or aerobic, to remove organic contaminants. So these are the two steps that are currently standard in wastewater treatment plants, at least in Europe. And the issue here is that they are not targeted at micropollutant removal. So that was not the aim when these treatment plants were designed. So you have very low removal efficiencies for example, pharmaceuticals of often below 50% of the influx. One way to upgrade these treatment plants is with a third stage targeted at micropollutant removal. And these are usually more advanced filtration steps, for example, using ozonation, membrane filtration, or something like distillation. And also the adsorption on carbon adsorbents, such as activated carbon or biochar, is in this stage. And in general, you can say that these all achieve high removal efficiencies of over 95%, always depending on the pollutant as well as on the adsorbent or the dosage. But as a general assumption, you can say that they work. However, the big disadvantage is that they are really costly, so they're very expensive. And that's why I'm looking at carbon adsorbents to see how this can be improved. So as I said, activated carbon is one of the benchmark materials for the removal of micropollutants. But the costs are currently the main obstacle for widespread adoption. So the only country I'm aware of that has mandatory removal rates is Switzerland to date. They upgraded their wastewater treatment plants, I think now 4 years ago. And also Germany and Sweden are starting this. However, the obstacles of high production costs of up to 10,000 euro per ton are quite an obstacle. Furthermore, activated carbon is usually produced from unsustainable feedstocks such as coal as a fossil material, or in some cases from tropical biomass such as coconut shells. Additionally, you have high operational costs for the separation of the exhausted adsorbent from the filter. Just imagine a wet carbon powder that you have to remove from a water phase. So that's usually done by centrifugation or another filtration step, so quite expensive too. And as a last point, you also have high regeneration costs for the adsorbent using conventional techniques, which means that often your activated carbon is directly burned as a disposal treatment. So my aim was to design a sustainable carbon adsorbent and specifically focus on the integration of the production, adsorption, and the separation properties of the material. And we can break that down to smaller research objectives. So the first one is that the biochar should be inexpensive, produced from renewable and regional feedstocks, and has a sufficient adsorption capacity. So I'm not assuming to be able to directly compete with the capacity of a fossil-based activated carbon, but at least it should be comparable. And the second objective, to decrease the operational costs of actually applying the adsorbent, is to produce activated biochars with enhanced magnetic properties to be able to separate the adsorbent easily from the water phase after use. So how to produce magnetic carbon adsorbents? So first of all, the goal is to enable easy separation from the liquid phase by applying an external magnetic field. So basically holding a magnet next to the water phase, and you will get the carbon adsorbent on the magnet and can separate it like this. So there's another problem with producing magnetic carbon adsorbents, which is that they're usually produced by the use of chlorinated or sulfonated iron precursors, so usually iron salts, different ones. And as we already can assume from the word chlorinated or sulfonated, they have an inherent potential for secondary pollution, both during the production and the application phase. And as an example, here's a picture from a recent publication from Damati et al., who did iron chloride pyrolysis. And on the right side, you see the chloride salt deposits. So either the chloride ends up in your pyrolysis reactor, which can cause several issues, or in the gas emissions, or in the worst case, on your biochar adsorbent, and will be released into the water phase when you apply it in the water. So alternatives, alternative iron sources are solid precursors. So natural solid precursors, for example, goethite or hematite. And in this study, we identified ochre, which is a residue from mine drainage treatment, as a potentially even more sustainable iron source, because you use a currently unutilized waste stream. So ochre is produced by draining abundant coal mines. So underground coal mines have to, you have to remove the water from rainfall and groundwater influx to keep the structure of a mine stable. So you pump water out, and this is usually mixed with minerals. So you end up with an ochre sludge, which you have to dispose of. And in the UK, this is around 4,500 tons per year of dry sludge. You can see that on the right. So that's the ochre that I used to produce my biochar. That's dry ochre sludge, and if you touch it, it will become powder. So the ochre has around 55% iron content, which is mainly from goethite. And the interesting thing, besides being an unutilized waste stream, is that ochre currently has landfill costs between $90 and $180 per ton. So if you use this material feedstock, you actually can make your production a lot cheaper. But iron is not only enhancing magnetic properties, but it also affects the product distribution and composition of your pyrolysis product process. So you change the pyrolysis yield distribution between solid, liquid, and gas fraction, which enables potential benefits for the process efficiency if you are able to estimate which fraction you can enhance and which one you can decrease in amount produced. And to give you an idea about the complex interactions of iron with the individual biomass constituents, there's a table from Collard et al. And if you're interested in iron catalyzed pyrolysis, I would recommend reading his paper, or a couple of papers from him, which you can find at the end of the presentation in the references. However, in this table, the interesting thing is you have these three main constituents, cellulose, hemicellulose here as xylan, lignin, and then a complete biomass. And on the right, you can see the estimated change in pyrolysis yield changes. So the char, if the char amount, the char yield increases, decreases, the amount of water in the gas phase, CO2, H2, CO, or the tar fraction. So it's a complex interaction with the individual constituents of biomass, which means that by careful selection of your biomass feedstock, you should be able to increase the, for your application, beneficial compounds, and therefore the pyrolysis efficiency. To achieve this, or to study this, we used two different feedstocks, so softwood pellets and wheat straw pellets, and mixed them with 5 and 10% of ochre prior to pyrolysis, which means we added around 2.5 and 5% of iron, so not a lot. You can see the feedstock on the right. And then we pyrolyzed it at 550 degrees in nitrogen and a two-step activation in at 800 degrees in CO2 afterwards. And then we analyzed the product yield distribution, so solid, liquid, and gas fraction. And additionally, we also used online gas monitoring to analyze the composition of the gas fraction. So for CO, CO2, CH4, and H2, which is sufficient to calculate the gas energy content to know if we can utilize this fraction for a more efficient pyrolysis process. On the right, you can see the reactor we used. So it's an infrared heated reactor. The gas stream, the gas exhaust is flown through 4 condensation traps to remove the condensable fractions or the tars before the gas fraction is analyzed by our online gas monitoring. And just a quick overview about the experimental section. So I looked at the production performance, so of the whole pyrolysis process. I characterized the biochar afterwards, and then I used the biochar to test its adsorption capacity for 2 emerging contaminants, which you can see on the right. One is caffeine, which we all know is the world's most widely consumed psychoactive drug, which we know when you drink it. And the other one is fluconazole, which is an antifungal medication, especially important in wastewater treatment because it has very low removal efficiencies and is commonly found at similar levels in the influx and effluent of wastewater treatment plants. So now to the actual results from my study. So here you can, at first we looked at the pyrolysis process. On the top left, you can see the lignocellulosic composition of the 2 feedstocks. So the main difference is that wood has a higher cellulose and lignin content, while wheat straw has a higher hemicellulose content and also a higher ash content, which is not shown here. On the left from these 2 columns, there's softwood pyrolysis with the top no ochre addition, the middle one with 5% ochre, so 2.5% iron, and the bottom one with 10% ochre addition. And what is interesting here is to look at the first peak of CO2 and CO, which is, if you go from the top to the middle to the bottom, which is significantly decreasing. And this first emission peak is usually typical for hemicellulose decomposition, which you can see is decreasing quite a lot, while just at higher temperature, so the x-axis is representing the pyrolysis temperature from 100 to 550 degrees. The second peak is increasing with ochre addition, which is referencing to cellulose and lignin decomposition. And that's something iron is known for, to increase the cellulose and lignin decomposition, but the most interesting part is the change in the hydrogen peak, indicated here in red. And you can see that the presence of iron is shifting the peak from 550 degrees down to around 400 degrees for ochre-added samples in the softwood feedstock. And most importantly, it's also decreasing the size or the amount of hydrogen emissions, which we can see on the table on the left. So here you have the total gas yield and the composition. SWP is softwood and WSP is wheat straw, and the number indicates the ochre, the amount of ochre added. And here you can see that with the ochre addition, the total gas yield increases quite a lot, which was assumed from the influence of iron. And while CH4, CO2 and CO all are relatively stable, the hydrogen is increased almost 10 times the amount. And an opposing trend is seen for wheat straw, which still has an increased hydrogen yield, but the total gas yield decreased significantly, about 20%. And here you can see that the feedstock high in cellulose and lignin produces sufficient amount of hydrogen to actually influence the gas energy content, which you can see on the right. So that's the lower heating value of the gas. In blue, the softwood biochars, and in green, the wheat straw biochars. And the red line indicates the limit for a self-sustaining pyrolysis run. So that means if you directly utilize your gas stream by burning it and heat the reactor with the energy from burning your gas, you can actually self-sustain your pyrolysis if you're above this red limit, which was previously calculated by Crombie and Nashek. And for the blue feedstock, so softwood, we can see that the increase in gas yield and hydrogen content significantly increased the gas energy content for about 40%. And most importantly, you produce excess heat if you use the gas on site. So you can use the excess heat for drying or other applications on the site, besides not needing any energy input for your pyrolysis reactor. The opposite was true for wheat straw, which was also expected due to the lower gas yield. The same emission pattern for the physical activation step in CO2. Here it is interesting that the iron is highly reactive. So this means that you have higher CO, so carbon monoxide peaks on the right, which means you're actually burning off your solid carbon from the biochar, which is not a good thing. However, that's the influence of putting iron in your feedstock. And on the left table, you can see the yields, the solid yields. In the pyrolysis process, you actually have higher yields with iron addition because you add some ash. And then in the pyrolysis plus the activation yield, you see a dramatic decrease in yield for the high ochre amendment, which is also indicated in the CO peak on the right. And most importantly, to see if our process is how sustainable it might be for carbon sequestration purposes. On the bottom, you see the total solid carbon yield, which decreased from 33% without ochre addition to 19%. To actually say if the whole process is beneficial or not, we have to take into account the total solid carbon yield that you see here, but also the increase in gas energy content as you offset fossil energy usually for heating your reactor. And if more importantly, you also have to check the adsorption performance, as this will determine your product quality. So here for some for the activated biochar characterizations of the solid product, you see some basic numbers, so carbon content, iron content, and also the magnetic susceptibility, which indicates how magnetic your biochar is. And to give you an example, here is our softwood pellet with 10% ochre addition, and my dirty hands will put a magnet next to it, and you can directly see it is quite magnetic, so it's not easy to actually get the magnet off again. And that also works in the liquid phase. So the magnetic susceptibility is high enough to actually use this biochar for magnetic separation. We confirmed the magnetic susceptibility by X-ray diffraction, as you can see on the top right. The red peaks are for the ochre amended biochar samples, and the purple peaks at the bottom are reference patterns for magnetite, and we can see it adds up quite well. So, and we don't see a peak for metallic iron, so the goethite was successfully transformed to magnetite during the activation. And on the bottom, you see another important characteristics of the biochar, which is the process distribution. Interestingly, the iron addition added pores in the size between 4 and 5 nanometers. So you can see in the dark, in the peak of the dark line, as well as some micropores between 1 and 2 nanometer. The pores between 4 and 5 nanometer are especially important for biochars in wastewater treatment, because micropores are usually used in gas filtration. In wastewater treatment, you need some pores that actually allow the contaminant to reach the micropore to be adsorbed. So that's a very beneficial characteristics in this case. to have a look how magnetite on a biochar looks like. Here you see again the softwood biochar with 10% ochre addition in a SEM image with equipped with a EDX scanner. So we see in the spectrum that these are magnetite, not from this spectrum, from the XRD, we know it's magnetite. From this spectrum, we see that these are the iron containing particles attached to the surface in a spherical shape. And now, last but not least, the adsorption capacity of our activated magnetic biochars. We used an commercial activated carbon as a reference material to see how good we are. So on the left, you see the fluconazole batch adsorption test. In blue, so the darker the blue, the more ochre content was added. And we can see we're still far off the commercial activated carbon, but more or less at 40–50% of the capacity. And what is also interesting for looking at the influence of iron addition on the adsorption capacity for biochars themselves, we see that we have between 70 and 100% increase in capacity with 5 and 10% ochre addition, which you can see on the table on the right. So just to remind that this difference to activated carbon still doesn't show that you can use the magnetic biochars, or you can separate the magnetic biochars by the magnetic field, which will give you a significant advantage in this case. So as a conclusion, or as conclusions, we showed that ochre addition can increase the gas energy content and enable self-sustaining pyrolysis. So that's often an overlooked part of iron doping, that you usually only look at the performance of the solid product and not at the process itself. And the lower biochar yield is balanced by increased adsorption performance, although an optimization of the activation parameters is necessary to actually produce this efficiently. The magnetic properties decrease the operation costs, as I said before, and there's a potential to optimize the production process by a careful feedstock selection based on the individual biomass components. So as we saw for wheat straw, iron doping doesn't really make too much sense. In the case of softwood, it makes a lot of sense. And if you're interested in subsequent experiments on the regenerability of these produced biochars, you can check Pierre Oesterle's previous presentations about hydrothermal recycling of activated biochars on our website, because these are the same biochars as used in this study. Yes, that's all from me. So thank you for listening, and I'm happy to answer any questions if there are any. Thank you. So now I have to ask the questions myself, I guess. Oh. So first question from Gilmore: how was iron incorporated into the biomass prior to pyrolysis? Basically I produced a water ochre suspension and mixed it with a suspension in DI water, and mixed it with the feedstock and let it soak, because the feedstock naturally soaks water. So that was all I did. Yeah. Why, if the H2 yield increases with ochre, it hinders the pyrolysis of being orthothermal? Not sure if I understand it correctly. So for increasing the gas energy content, not only the hydrogen is important, but more the methane yield, which decreased for wheat straw. And that was the main reason why it was not self-sufficient. I hope that answers the question. The forms of iron in biochar after pyrolysis. I'm not sure. Unfortunately, I didn't check that after the pyrolysis step. I know that the biochar is highly reactive. So if you take it out of the reactor at 40, 50 degrees and expose it to air, it will directly oxidize. So I guess it's a highly reduced form of iron in there at this point. I think the CO2 activation actually stabilizes it as magnetite. Did you do functional groups analysis? Yes, you can read that in the hopefully upcoming paper soon, but there was nothing too interesting there. Did you observe any corrosion or deposition during biochar conversion, as seen with iron salts earlier? The only no corrosion. I mean, I used a quartz glass reactor. So the only deposition I realized was iron or ochre powder, which fall through the biomass. And when you try to burn out your glass cylinder, it will get incorporated into the glass. So that is something that I realized, but that was usually because you always have some ochre powder sticking, but only slightly sticking to your biomass and not really attaching to it. If the iron evaporate during pyrolysis, I don't really know what you mean with that. Dissolved iron can be challenged. So I checked the biochars in leaching experiments, and we did not observe any real iron leaching. So I hope that won't happen, or at least I couldn't find it. Yeah, please, if you have any more questions, let me know. Other than this, because we already